Hi, my name is Rich Hickey, and I'd like to introduce you to Datomic. Datomic's a new database, and it's focused on bringing the data manipulation power normally possessed only by database servers into applications, and combining that with an information model that incorporates time. And it's a database design that leverages the fact that hardware and architectures have changed substantially since databases were first invented. In this talk, I'm going to describe why we built Datomic from two perspectives. The first is the architecture, and the second will be the data model. If we look at architectures from the past, we see and understand, I think, the client-server model, where the server has all the brains. It knows how to handle queries and process them. It handles transactions. It ensures consistency, and it manages storage. And applications are relatively dumb in this model. They rely on the server to do most of the work. Of course, as you get more applications, you end up with a lot of pressure on that server to scale it. So you might cluster your servers or replicate them in an effort to provide more processing power as you have more application servers. Of course, even that is very difficult to do and have scale well, so you might then go and shard your server. At this point, though, we start to lose some of our power, right? Because each shard has only half a brain. It doesn't really have the capability to process queries or transactions that cross over the entire data set. Finally, you might adopt one of the new key value stores, and at this point, no one has a brain, right? There's no query power left. You're giving up transactions and consistency. While there are lots of attributes of these key value stores, being a database isn't one of them. So I think it's better to start talking about them as distributed storage services, at which they're quite capable and are interesting components of bigger systems. So how do we get the power we used to have when we had a whole database back as we move to these more distributed architectures? The approach we take in Datomic is to put the brains back into the system inside the applications, and essentially to give every application its own brain. And you might think that this would be sufficient. Obviously, the first part of a brain would be the query engine. But in the end, this doesn't recover all of the power of the database, because if every application is able to interact and store against the storage service independently, there's no way to make that consistent or transactional. And for the kinds of systems that we're targeting with Datomic, we value both consistency and transactions. We want to recover them. The way we get that back is to stop having the applications write to storage and to change it so they can only read from storage, and to introduce a new component that we call the transactor. And the transactor's job is strictly to coordinate transactions and to facilitate the consistency there. And by introducing the transactor, we get back both transactions and consistency. So applications that have novelty or change that they want to introduce into the system will send it to the transactor. The transactor, in turn, will make sure that it makes it into storage and will reflect it back to the other applications so that everyone has a current view of the world. And this is basically the way Datomic works. So we talked about getting your own brain. What does that actually mean? Well, it means that you get a query engine that you can embed right into your application, as well as the communication infrastructure for participating in the service, and a memory engine which handles the caching that's required. And when you put this Datomic library in your application, we consider it to be a peer, because it is as big a part of the database as any of the other parts. The big effect that happens when you do this to your application is it feels as if the database is local, and effectively it is, right? It can obtain anything that it needs to process queries on demand from storage, and you lose the round trip nature that you usually have with a client-server database. There's no problem with getting some data and immediately turning around and getting some more. There's no round tripping associated with that. As your working set gets cached, eventually all your interaction with the database stops crossing the network at all. The other big effect of things being local is that you have isolation from other applications and other participating servers in your system. Right? There's no problem with running a long-running query because you're not taxing some shared server resource. You're using your own processor, which means if you want to set up a system with a bunch of application servers that service the web and then a bunch of analytics machines that run long-running processes, they can all cooperate fine. You don't have to copy stuff into an external analytics system in order to keep the load from getting in the way of your transaction processing. Another part of having a brain is having a logic engine. And as we said, you get this declarative query engine that you can use both for traditional query, search jobs as well as for ordinary business logic. There's a lot of power in moving from conditionals in your programming language to a declarative language for business logic. The query language that we incorporate in Datomic is called Datalog. And it's very simple. It just uses rules and data patterns, and the data patterns you would recognize if you've done pattern matching or seen it in any kind of programming language. The important thing about it being declarative is that joins are implicit and that the meaning of your program is evident. And this is really a very powerful thing, and it's an important objective of Datomic to bring this to applications, not just for the database, but because we brought the database local, it means that this query engine is also local and can be applied to non-database sources. So you can use Datomic's Datalog to process collections in memory or combinations of the database and collections. And that's a lot of power. Another characteristic you would normally associate with having a brain is being able to perceive things. And as we saw, the transactor pushes out to the peers all the new transaction information. And inside your process, you can obtain a queue of these transactions. And what you'll get over that queue are not just your own transactions, but all the transactions in the system. As a result, you can take that transaction information, and as we said, because the query engine can deal with any kind of data, you can just pass the transactions into the query engine in order to filter out the information or events that you might consider interesting to your particular application, and therefore make an application that's reactive, and you don't have to do any polling. Consistency is really important. As we saw before, the transactor ensures that when you have change or novelty, that's done with traditional ACID transactions. So when you add new facts, you have transactions covering the consistency. But consistency is also important for the decision-making side of your application, both for reads and for queries. And it's important, I think, to make sure you deliver consistency to applications for those purposes without using transactions, because transactions require coordination and perception and decision making normally doesn't. So we want to make sure that we don't need it in our system design. Instead, what we'll use for consistency is immutability. And that takes two forms in the system. The first is that when you interact with the database in your application, it's not like you have a live connection to a morphing thing. What you can do at any point in time is just ask the connection for the database, and what you'll get in your application is a value like 42 is a value. And that's a stable thing that you can issue queries upon and compare to other values of the database. The other thing you get out of taking an approach to consistency based upon immutability is that the data that's put into the storage service is immutable and therefore subject to extensive caching, because we're never going to go back to a data segment and change it. The final part about giving you a brain is making sure that that brain is connected to the rest of your program. And there's a couple of ways in which we take care of that. The first is that all of the interaction points with Datomic are based around ordinary data structures. They're not intricate APIs or complex syntax and strings in a foreign language. Transactions and rules and queries and results are all represented as ordinary lists and maps that you can program against and create with your programming language. In addition, there's the extensibility you would expect to add types and predicates. And the final part of programmability that we offer is the ability for queries to invoke your own code. This is sort of the ultimate extension point. And again, it's enabled by the fact that it's local, right? There's none of the complexity of sending your own jars over to the admin so that he could please install them on the server, which everyone knows is never going to happen. So you can invoke your own code from the declarative logic engine. All right, let's talk a little bit about the data model. And in particular, when you talk about databases, you often think that it's the domain of memory and records. That's what databases are for, record keeping. But it's important to remember that these words existed before there were computers and what they used to mean then. In particular, we associate memory with mental memory, and the characteristics of mental memory that are salient are the fact that it's associative and open. In particular, you would contrast that with a memory that was oriented around particular addressable cubbyholes. We can also talk about records and record keeping from the days prior to computing. Then records were enduring. You wrote them down, and when you had new records, you took out new paper and wrote them down. You did not go back and erase things and overwrite them. Unfortunately, that's not the way computer systems work, but it could be, and I think now is the time for us to start implementing these two things correctly. So what have we got right now? Unfortunately, what we have right now is something I'll call place-oriented programming. And whether you're talking about imperative programming languages utilizing memory or databases, most of the things that we have to use in programming are oriented around taking new information, finding the place where it goes, and putting it there. And when you're interested in a fact, going to the place where it would be stored and grabbing it out of that. And it's understandable why early computers did this, right? They had small amounts of RAM and tiny disks, and of course, they had to reuse those things and almost immediately do so. But in the time since I've been using computers, RAM and disks have increased in capacity 1,000,000-fold. And I think it begs the question as to whether or not we should be taking the same approach to them as we did when they were 1,000,000 times smaller. So let's contrast places with facts, because I think facts are the model we want to use moving forward. I think everyone's familiar with a table in a database that uses tables, where there's some key and there are columns, and the intersection between a key and a column is where that information goes. And so if we want to say Fred's street, we go and find Fred and go over to street, and we see that Fred Street is Spring Street. And when Fred moves, typically what happens is we go back to that same place and we remove Spring Street and we replace it, in this case with Maple Street. So the fact that Fred lived at Spring Street is now gone. It's the same thing with documents. They're really not different in this way, right? You'll have some document structure, and somewhere nested inside it is the place where we encode Fred's street. And when Fred moves, we go to that place and we replace it with Maple Street. We can contrast this with facts. And if we wanted to try to figure out the smallest way to talk about Fred's living on Spring Street, we could say that Fred's street is Spring Street. And if we say that, we can say that's a fact, but it's actually not a fact for all time. In fact, Fred Street is Spring Street only at a particular point in time, and from that point in time until Fred moves. And so we encode Fred's street as Spring Street at a particular point in time. That's what T27 is here. We can represent time using the transaction that encoded that fact. Then time passes and Fred moves. Instead of going back to that place and replacing Spring Street, we just record a new fact because this fact is distinct from the other fact. Fred's street is Maple Street starting at some later time. And the key thing to take away here is that new facts are placed in new space. They don't go back to the old space. And so what's required when you start using a system based around facts is that you have some way, the system needs to know, for instance, that you don't live at more than one street at a time, and it needs to make it efficient to find out where does Fred live right now. And that's what Datomic does. So Datomic is a database of facts. And we use only a single representational construct for storage, which we call the datum. And it has four aspects to it: the entity, the attribute, the value of that attribute or values, and the transaction at which point in time that fact was recorded or retracted. The only schema that exists in Datomic are the definitions of the attributes. So attributes have types, they have names, they have cardinality and things like that. And that's all you need. You don't need anything more structural than that to describe a schema. So I think everyone that looks at alternative databases is interested in what I'll call adaptability, the ability to change your mind and address changing requirements. The first thing I think people seek is an easy way to deal with data that's not rectangular, sparse data or irregular data or hierarchical data. And this concept of a datum makes it very easy to represent these different shapes of data. So that's straightforward. The other thing that you want to be able to do are encode both single and multi-valued attributes without having to introduce things like intersection tables and intersection records. And we support multi-valued attributes directly. The more important thing and the more difficult thing related to adaptability and really agility is to avoid structural rigidity pervading your application. So what do I mean by that? I mean that structural rigidity is something you would measure as the extent to which, say, your choice of tables or the organization of your documents invade your application and become something that's difficult to change later. This actually has nothing to do with recording your schemas, right? If you use a document database that doesn't require you to record your schemas, you still can end up with tremendous structural rigidity because you've married the structure of the documents that you've stored in your database, and it's not going to be easy for you to change their organization later. So the beautiful thing about a datum is that it doesn't have any structural implications. So we like to say that nothing pivots like a datum. Finally, we talked about time being built in the data model. We already saw that every datum retains the transaction in which it was recorded. Those transactions are totally ordered. So the transactor actually does a complete serialization of all transactions. And it ends up being the case that it's faster to serialize transactions than it is to make a transaction server that's multi-threaded and uses locks to coordinate overlapping transactions. Transactions themselves are first class. So a transaction is an entity like any other in the system, and you can record facts about transactions. So it's easy to record who entered a piece of data. When it came in is automatically recorded, as well as what its provenance is or any other kind of characteristics. You just make those facts about the transaction itself. The other more interesting thing, and possibly more difficult to get your head around, is the fact that given that a database is a value and that we keep the past, it's possible to get the value of the database as of a different point in time, like a point in time in the past, or to get a window of the database since a point in time or between 2 points in time. And this is really powerful because by obtaining a different value of the database, you can reuse your application logic and queries to do what if or as of kinds of calculations without passing time around as a parameter everywhere. So I think the net result of this combination of features and architecture is a system that's significantly simpler and more powerful than what we were doing before. Decomposing the database into a composition of services makes it significantly more flexible. Facts are simpler than places and easier to make consistent. And adding declarative programming to application programmers' toolkits gives them a lot more power than they had before for manipulating data, which is what database programming is all about. I hope you found this interesting, and thanks for listening, and I hope you get to try Datomic.